Guys, so we are starting a video today on inverses and one-to-one functions. So words you've probably heard before. Here's our definition. I know it's in your notes. But what an inverse function does is it reverses what the original function has done. So if we take an input and get an output out of it, so if we take f of 3 and we get 7 as our output, and then if we put 7 into the inverse, then it will give us 3 again back to square one as our output. That was probably a little confusing. We're going to talk a lot about that the next time I see you. All right, so the inverse is a rule where the output of the original function produces the corresponding input. So really the kind of a clear way to think about it is through trigonometry. All right, so if our original function says the sine of 30 equals 1/2, then the inverse function says that the inverse sine of 1/2 takes us back to our original input, which was 30 degrees. All right, so we know kind of common inverses. The trig functions have common inverses that you've used a lot. X squared and the square root function are very common inverses. We're going to talk a lot later this year about exponential functions and logarithmic functions being inverses. So really what an inverse function does is it undoes what the original function already did. Okay, so it's not in the -1 power, as I've said a bunch of times already in this video. F inverse is how it's read. F with the -1, superscript there is F inverse. So the domain of the inverse is equivalent to the range of the original function, and the range of the inverse is equivalent to the domain of the original function. So kind of, again, back to trig, that's another complicated sentence. For trig functions, when we think about the sine of x, well, I guess I'll write like this: f of x equals the sine of x. Our input here are angle measures, whether it's in radian or degrees. Sine of 30 degrees, sine of 180 degrees, sine of pi over 6 radians. So the domain of the trig functions are degrees, they're angle measures, and the range are just ratios, constant values. So then if we're talking about the inverse trig function, it's flipped. The domain are the ratios, and the range would be the angle measures. All right, so the input is flipped with the output. Kind of long story short. Okay, so to find inverse algebraically or graphically, all we're doing is switching the domain and the range. We're switching the x's with the y's. So if there's an ordered pair, x, y becomes y, x, excuse me. So that's how we're going to find the domains algebraically and graphically. All right. However, not all functions have inverses. So functions that have inverses are called one-to-one functions. So a one-to-one function is a special type of function where each element of the range has only one corresponding element of the domain. So it must pass the vertical and the horizontal line test. So we're usually used to talking about functions where each element of the domain produces only one element of the range. So that's the vertical line test. One-to-one functions have to go both ways. Each element of the range can only have one possible element of the domain to get you there. So kind of an easy example to see is the function f of x equals x cubed. So no matter where I go on this graph, if I want to find what's f of 2, there's only one output that gets me there. Same thing for any of these values. But it also goes the other way. If I say, okay, how did I get, well, it's not on the, well, let's say 1. How did I get 1 as an answer? How did I get an output of 1? The only way to get an output of 1 is if the input was 1. So it's very different from x squared, where 2 outputs could have the same input to get you there. Okay? So a really nice example that I've kind of found to help us think about one-to-one functions is this vending machine. So I want you to just take a second to think, is this a one-to-one function? All right, so it's a little hard to see, but first of all, what I would think about is this definitely would pass the vertical line test. If I look at each one of these buttons, there's only one thing that's going to come out when I hit that button, right? If I hit B1, the only thing that's going to come out is this type of chip. So I'm not going to hit B1 and like not know what I'm going to get. So that's how we know that it's just a traditional function. Each input can have only one output. But remember, it has to go both ways. Each output can only have one input to get us there. So if I say, all right, for this vending machine, if I want Lay's chips, there's two spots that those Lay's chips show up. So I'm not sure if I tell you I got Lay's out of this machine, you can't guarantee what button I hit to get them. So that's not an example of a one-to-one function. If I remove these Lay's from the vending machine, and that's what we're going to talk about in a second, if I change my domain, now we're getting closer to be a one-to-one function. It looks like I have to do the same thing to a couple other items in here. But that's what we're going to have to do to make functions one-to-one. All right, so let's talk about that. There's our graph, f of x equals x squared. The domain of this function, excuse me, is all real numbers from negative infinity to positive infinity. The range looks like 0 is okay, so we include 0, and we can go all the way up. So like I just mentioned on the last page, if I put in 2 into my function, there's only one answer that can come out of it. So this function passes the vertical line test. Each input, so if I do my little vertical lines, each input has only one output that goes with it. But if I say, all right, let's say our answer was 9. Let's say our f of x equals 9. There's two ways, and I guess we can think about it like this. F of x equals 9, so I'm going to say that. There was two ways I could have gotten 9 as an answer. I could have had it as positive 3, and I could have had it as negative 3. And that makes sense, right? If we were solving this for x, all the solutions, we'd have to say x equals plus or minus 3. But if we're just investigating this, if we're looking at this as just a function, that's why sometimes you will see just x equals 3 show up. All right, so I'll say that again. If we're looking at this as just the inverse function, we have to exclude that other value. We need this to be a one-to-one function. So what we're going to do today, what we're going to talk about, is restricting the domain. So if I were to just to kind of clip off this half of my function, if I were just to kind of cross that off, now it's one-to-one. Now if I say, okay guys, how did we get 9 for an answer? The only way to get that answer would have been positive 3. All right, so we'll come back to that in a second. But if we're looking at this graphically, this is kind of a really nice way to tie it together. If we're looking at this graphically, we switch the x and the y values. So what transformation, if you think back to geometry, what transformation happened when we went from xy to y comma x? So a lot of these rules, a lot of these transformations you did back in geometry, reflecting over the x-axis where we negate the y, reflecting over the y-axis where we negate the x. This has a lot to do with the transformations we've done on functions, and it has a lot to do with the inverse. So what transformation is in geometry is found by switching those two coordinates, switching that ordered pair. That is a reflection over the line y equals x. So if we ever wanted to find an inverse graphically, all we have to do is reflect over the line y equals x. So if we graph the inverse of the function y equals x squared, and this is in your notes, so you can see that here. So notice how once we do that reflection, now we all of a sudden have a function that doesn't pass the vertical line tests. So that's why we have to make these functions one-to-one. So if we do the reflection, it still passes that vertical line test. So kind of the shortcut, and that's, I don't want to kind of overthink it, but that's why these original functions have to pass the vertical and the horizontal. It's so we don't have to always graph it. So if we reflect that over the line y equals x, that's where this vertical line test kind of comes into play. All right, so if we're just looking at the original function, it has to pass the vertical and the horizontal line tests. All right, so I hope that makes sense. But here's why, when we go back to Unit 1, yeah, the very first day of Unit 1, This is why we talked about restricting domain. So it's another reason, aside from keeping it in real numbers, it's another reason why we restrict the domain. So like I showed you above, if we just kind of clip off this side of our function, we still have all the answers we need. We still have like all the outputs that match with the inputs. We're just getting rid of those negative kind of like extra values that we don't really need. So if we restrict the domain to the numbers 0 through infinity, it also makes our inverse a one-to-one function. So this y equals x squared. If I look at this, let me try to go through the dots I made. There's my, close enough. There's f of x equals x squared for the values only 0 through infinity. We can also see how this makes our inverse function a function as well. So there is f inverse of x, which we know is the square root function. And we're only looking at the positive half of that. So this is not the case where we're doing the plus or minus, because that minus would give me the values below here as well. And that's where we can't let happen for an inverse function. Okay, so that's kind of our background on what inverse functions are, what we have to do to make something an inverse function. All right, so I hope that makes sense. That's how we're going to look at them graphically. To find an inverse function algebraically, just the same thing we did before, just like the same thing we did graphically, we're going to switch the x's and the y's. So f of x equals 2x minus 5. If I want to find f inverse of x, what we have to do is switch the x's and the y's. So remember, this is kind of like a y, right? This is kind of like a y. So what we're going to do is switch the x's with y's, just like we did graphically, and then resolve the equation for y. I could even call this y inverse if that helps you see it, but we don't need to. I don't want that to kind of throw off your algebra. So we add 5 to both sides. This is a piece of cake. Plus 5, plus 5. You don't really have to show that step for me. You guys know that. We have x plus 5 equals 2y. Divide both sides by 2. And we have y equals x plus 5 over 2. And you could split that up into a fraction if you want. So our inverse function, after switching the x's and the y's for this first one, we have f inverse of x equals x plus 5 over 2. All right, so if you want, you could grab your calculator out. You could open up Desmos real quick. And if you graphed this function, and then you graphed its inverse, they should look like a reflection over the line y equals x on your graph paper. Okay, so that's how we're going to do it. So this second one, a little bit more going on. All right, so same starting point. We want to find g inverse of x. All right, so remember, that's like a y. So we're going to switch our x's with our y's. I missed one, didn't I? Yes, I did. And we are going to resolve for y. So why don't you guys try this one out on your own for a few minutes. See how you do. Let's test our algebra skills from last year. Then when you unpause, I'll show some of my work. All right, so try that out now. All right, so let's see how we did. First thing I want to do is get rid of that fraction. So since there's an equal sign, I can multiply by anything I want. I'm going to multiply by y minus 3 on both sides. So those divide out, and then we're just left with this step here. I then distributed that x through to both terms. So I have yx minus 3x equals 2y plus 5. Here's where you got to be really careful, guys. I can't just subtract 5 and divide by 2. All right, I can't solve for y in terms of y. So I can't solve for y if there's another y on my other side. So that's kind of like if a teacher asks you to define a word in English class, you can't use that word to define the word itself. So our next step, if you got stuck here, was I got all the y's on one side. So I subtracted 2y from both sides, and then I added 3x to both sides if you didn't follow my step there. But I got all the y's on one side of the equation, and now we're pretty much set up. So I factored the y out. Divided both sides by x minus 2. And that's how I got my answer. All right, so we're going to learn one more skill next class together. We're going to practice a bunch of these. Like I mentioned before, the big thing so far this unit is those transformations. So please don't hesitate. Come on to a Zoom, talk to your classmates. All right, please let me know if you are having any trouble with those transformation rules. All right, see you guys.